what if the physical weight of your own body, like the actual mass tying you to the chair you're sitting in right now, what if that isn't actually a thing?
I mean, it completely upends our entire standard intuition about reality.
Right. Because we're taught to view the universe as this collection of, discrete objects.
Exactly. Things obeying entirely separate rules. You have geometry handling the shape of space over here, right?
Yeah, and then quantum mechanics dealing with the weird behavior of subatomic particles over there.
And then you have particle physics sorting out all the heavy stuff in the basement.
Right. For decades, science has basically treated reality like a house built by 100 different contractors.
Contractors who never actually spoke to each other.
Literally never. And we just accept that the doors between those rooms are permanently locked. But today, we are blowing the doors off the hinges.
We really are.
So, welcome to the deep dive into the source material. We are unpacking a truly groundbreaking paper today.
It's titled Partial Spectral Closure, Fractals, Recursive Geometry, and the Ontology of Structural Completion. Such a mouthful.
It is, yeah. And we're also looking at its accompanying conceptual diagram, the architecture of closure.
Right. And our mission today, for you listening, is to show you how fractals, discrete quantum states, the forces of nature, and the literal mass of a physical particle all emerge from one single, highly elegant concept.
And that unifying concept is closure.
Closure, yeah.
And to understand everything that follows, we really have to define what closure actually means in this specific physical framework.
Okay, let's unpack this. What is it?
Well, it's the degree to which a structure or a process or an operator resolves into a stable, admissible form.
A stable form.
Right. Think of it as the universe's relentless drive towards structural completion and stability.
So the universe just basically hates unfinished business.
It literally cannot tolerate it. And what's fascinating here is that this framework takes fractals.
Right, which we usually just view as like rough geometry.
Yeah, anomalous, rough geometry, or just pretty mathematical oddities.
Like trippy dorm posters. Exactly. But it takes them and places them at the very foundation of how physical reality completes itself. It gives fractals this profound ontological purpose.
Wow. So if you're listening to this and you've ever felt overwhelmed by how disconnected modern physics seems, or if you're just insanely curious about why we live in exactly 3 dimensions instead of, say, 4 or 2, this deep dive is going to give you a massive aha moment.
It really changes everything.
I guarantee you'll not look at the physical objects around you the same way ever again. So let's start with fractals.
Let's do it.
When most people think of a fractal, like we said, they think of zooming infinitely into the Mandelbrot set on a computer screen. We're taught they're just infinitely complex, jagged shapes.
Right, because the classical view is purely descriptive.
Just what they look like.
Yeah, exactly. It tells us what they look like, how they scale, how a coastline gets longer the closer you measure it.
Right, the coastline paradox.
But this paper completely redefines them. It proposes that fractals are essentially partial closure structures.
Partial closure structures. Okay, what does that actually mean?
It means they are recursive domains that attempt to close, that approach completion, but they never fully resolve into an interdimensional manifold.
Okay, let's make sure we ground this because that's a lot of math words. When we say an interdimensional manifold, we're basically talking about the clean, perfect dimensions we learn in grade school geometry, right?
Yes, exactly.
Like a perfect 1D line.
A smooth 2D plane.
Or a solid 3D cube. Those are full integers. 1, 2, 3.
Right. In the language of this paper, an interdimensional manifold represents a completed closure regime.
Because it finished the job.
Precisely. A smooth 2D plane has successfully and completely filled two-dimensional space. There is zero ambiguity.
Okay. But a fractal isn't an integer.
No. A fractal is a physical or mathematical system that attempts to close space, but it stabilizes before it finishes the job. It finds this bizarre fractional equilibrium.
Right. And the paper actually introduces a specific formula to measure this called the closure ratio.
Yes, the closure ratio.
It's written as C equals log n divided by log s. I want to break this math down because it actually paints a really beautiful picture.
It's surprisingly intuitive once you see it.
Right. So n is the number of self-similar pieces you break a shape into, and s is the scale reduction factor, like how much you shrank those pieces compared to the original shape.
Right. Now, mathematically, this ratio is what we conventionally call the Hausdorff dimension.
The Hausdorff dimension?
Yes, but the paper's thesis is that this non-integer dimension is actually measuring the exact degree of achieved geometric closure.
Okay, let's walk through the paper's primary example for this.
The Cantor set.
Oh, perfect example.
So if you want to build a Cantor set at home, You just draw a straight line on a piece of paper.
Right.
Now, erase the middle third of that line. You're left with two smaller line segments, right?
Exactly.
So your number of pieces, your n, is 2. And because each of those new segments is exactly 1/3 the length of your original line, your scale factor, S, is 3.
So you just plug that into the formula, log 2 divided by log 3. And that comes out to approximately 0.6309.
Which forces us to ask, what does 0.6309 actually mean physically?
Because it's not a whole line.
Right. In a classical sense, it's just a number. But in the closure framework, the Cantor set is a structure that is roughly 63% closed as a one-dimensional manifold.
Wow.
It is a system that tried to become a solid line, failed, but instead of vanishing, it's stabilized at that precise fractional equilibrium.
I mean, I'm picturing an architectural project here. Like, you're building a bridge across a massive chasm.
Okay, I like that.
A full, solid 1D line is the completed bridge. Traffic can flow smoothly.
Right.
The Cantor set is a bridge where the construction crew just, stopped working at exactly 63% completion.
Yes.
But here's where my brain totally snags. If a bridge is only 63% built, it collapses into the river.
It does.
Gravity and entropy destroy it. So how does an incomplete mathematical structure, like an incomplete physical dimension, survive in nature without just dissolving into total chaos?
Well, the answer lies in the balance of forces within the structure itself.
Right.
Fractals survive because they hit an incredibly delicate equilibrium between geometric replication.
Which is the building of the bridge.
Exactly, and wave oscillation.
Wave oscillation,
Right.
like vibrations.
Right, the natural vibrations that the structure can support. The paper beautifully terms them the disciplined mathematical signature of incomplete manifold completion.
That is quite a phrase.
It means they occupy the critical boundary regime between a smooth, infinite continuum and discrete, locked-in stabilization.
Oh, which totally explains why we see fractals in nature exactly where chaotic systems are trying to find order.
Yes. Think of some examples.
Like the jagged branching of a lightning strike burning its way through the atmosphere,
Yeah.
or the way water percolates through porous rock.
Perfect examples. The system is trying to fully close the space, right? But the environment disrupts it.
Right, but organized structure still manages to survive in this 63% or 1.26 dimensional state.
Yes, those are critical transitions. Settings where full closure is completely impossible due to environmental constraints, yet total disorder doesn't win either.
But this brings up a crucial mechanical problem, I think.
Oh.
Yeah, the movement problem.
Right, right.
If my 63% completed bridge is somehow magically floating there, suspended in partial closure, how does anything actually travel across it?
Right.
Like, how do waves or heat or energy move through a space that is literally fundamentally incomplete?
And that exact question drives the second major revelation of the paper.
Which is?
The dual life of dimensions.
The dual life. Okay.
The text insists that we have to stop thinking of dimension purely as a geometric shape. Dimension is not just a geometric statement about where things are.
Right.
It is a spectral statement about how things can vibrate and move.
Okay, let's clarify spectral for a second. We're talking about a spectrum of frequencies, right?
Yes.
Like the distinct notes the guitar string can play, or the specific ways a physical space can naturally vibrate.
Exactly. We are talking about the admissible eigenmodes of a space.
Eigenmodes?
Yeah. To truly understand any physical domain, you must measure both its Hausdorff dimension,
Which is the geometric shape we just discussed, like the 0.6309 of the Cantor set.
right. You measure that, and you measure its spectral dimension.
And what is that?
That dictates how wave-like energy populates and travels through that specific geometry.
Because normally we just assume they match, right? Like if you're sitting in a regular room right now, you just assume the 3D geometry of the room perfectly matches the 3D sound waves bounce off the walls to reach your ears.
And in our normal, smooth, interdimensional world, they do match perfectly.
Okay.
This is codified in physics by something called Weyl's law.
Weyl's law.
Yes. In a smooth, interdimensional manifold, Weyl's law dictates that the growth rate of eigenmodes...
Wait, what's a growth rate of eigenmodes?
It's just the number of different vibrations that can mathematically exist in that space as the frequency increases.
Oh.
Weyl's law says that growth rate perfectly matches the geometric dimension. A two-dimensional drumhead supports a two-dimensional growth rate of vibrational modes.
And the paper calls this complete spectral closure.
Yes. The physical space and the energy traveling through it are in total harmony.
The architecture of the room provides exactly the right amount of space for the sound waves to explore without tripping over themselves.
Exactly. But the moment you introduce a fractal, that harmony shatters completely.
Because it's jagged.
Right. In recursive, infinite jagged domains, the geometry and the wave dynamics decouple. Weyl's law deforms.
Wow.
The eigenvalue counting function, the mathematical rule tracking how many waves can fit inside the space, follows a modified law. The number of modes grows proportionally to the power of dies divided by 2.
Where D's is the spectral dimension.
Exactly.
So wait, a fractal has a physical shape, a geometric dimension, but the actual energy traveling through it experiences a completely different dimensional reality.
Yes. The physical space is screaming one set of rules, and the waves are forced to obey another.
That is wild.
And this hidden spectral dynamic is exactly why certain fractal dimensions appear repeatedly in nature.
Because I've always wondered about that.
What's fascinating here is, why does a Koch curve always stabilize at a dimension of roughly 1.26?
Right.
Or why does a Menger sponge lock in at 2.73? They appear in completely different physical systems.
Like dielectric breakdowns.
Or critical fluid clusters. Or diffusion-limited aggregation.
So they aren't just random decimals the universe stumbled into.
Not at all. They are optimal balancing points. They are underlying universal scaling laws.
Wow.
A specific physical fractal dimension emerges when two competing forces negotiate a truce.
There's forces.
The structural replication of the physical geometry.
The building of the space.
Right, and the eigenvalue rescaling of the waves trying to survive inside it.
The energy trying to move.
Exactly. Dimensionality itself is a closure residue.
A closure residue.
Yes, it is the numerical footprint left behind when a system tries to balance space and energy but is forced to halt before reaching a whole integer.
But this raises a huge problem, doesn't it?
What do you mean?
Well, if the space and the waves are constantly negotiating, what happens when the negotiation fails?
Oh, right.
What happens when the physical shape of a space and the waves trying to travel through it fundamentally disagree?
Right. The paper formalizes that disagreement as the closure defect.
The closure defect.
Yes. It's a highly specific, measurable quantity defined by a simple formula. Delta C equals the absolute value of the geometric Hausdorff dimension minus the spectral dimension.
So it's literally a mathematical measurement of how out of sync the universe is with itself in a localized area.
Precisely. It quantitatively measures the mismatch between how space scales and what modes it allows to exist.
Okay, let's look at the mechanics of this.
Sure. When the defect is exactly 0, you have complete spectral closure. Heat spreads evenly, gas diffuses normally through a room.
Right. I used a plumbing analogy earlier, but I feel like I need to refine it because fractals are just so weird.
Go for it.
Imagine a massive, sprawling mansion with infinite hallways. That's your geometric Hausdorff dimension. It's
Whoa.
incredibly vast.
Right.
But the spectral dimension is the ability of people to actually walk through the house. If the defect is 0, the hallways are wide, clear, and logically connected. You can walk anywhere. Normal diffusion.
I like that. But in a fractal mansion,
Right.
the hallways are infinite, but they constantly dead end. They turn into microscopic, twisting capillaries that loop back on themselves.
Wow.
The physical volume of the house is still massive, but the transport efficiency is an absolute nightmare.
Right. So if I try to walk through it, I'm constantly hitting walls, turning around, getting stuck in infinite loops. The space is physically there, but the movement is totally restricted.
Exactly. In physics, we call that anomalous transport.
Anomalous transport.
Yes. When you have a moderate closure defect, things subdiffuse. Heat struggles to navigate the recursive geometry.
Like a liquid poured into a porous medium.
Right, it doesn't spread smoothly. It creeps along convoluted, highly resistant pathways.
And what if the defect goes off the charts? Like, what if the mismatch between the size of the mansion and the layout of the hallways is so extreme that you take one step and are instantly trapped?
The paper explicitly addresses this extreme limit. If the closure defect becomes too large, the system undergoes spectral trapping.
Spectral trapping.
In condensed matter physics, this is known as Anderson localization.
Anderson localization. Oh, wow, that's a massive concept in material science.
It is.
It's why certain metals that should conduct electricity suddenly become complete insulators if their internal atomic structure is too disordered.
Exactly. And the closure framework explains why Anderson localization happens.
Tell me.
The waves, the electrons trying to move through the metal experience such a severe mismatch with the disordered geometric support that they destructively interfere with themselves.
They cancel themselves out.
Yes, they become completely trapped, frozen in place by the geometry. The universe simply says, these waves are no longer admissible in this space. Transport halts.
That is incredible. The defect literally freezes energy.
Yeah. But nature isn't always uniform, right? I mean, a turbulent storm doesn't have just one level of disorder.
No, it doesn't. Which brings us to multifractal spectra.
Okay.
In highly chaotic systems, like violent fluid turbulence, the closure defect isn't just a single uniform number. The mismatch is distributed across different scales.
Creating a whole spectrum of varying defects.
Exactly. To use your analogy, the house doesn't just have one type of bad hallway.
Right.
It has millions of different bottlenecks of all different sizes depending on which room you enter.
And the universe cannot stand that kind of complex imbalance. It wants to resolve the tension.
It desperately wants to resolve it.
So what does it do?
It initiates a closure cascade.
A cascade.
It transfers the closure defect from large, highly coherent macro scales down to small, dispersed, entropic microscales.
Okay, think of a massive waterfall crashing into a river.
Okay, good analogy.
At the top, you have this huge, coherent, sweeping current of water, a massive concentration of closure defect. It's totally out of balance.
Right.
As it hits the rocks, it breaks into smaller currents. Those currents break into violent eddies. Those eddies break into tiny, chaotic swirls, tearing themselves apart until the kinetic energy just dissipates as invisible heat into the water.
Yes.
The waterfall is physically cascading the mathematical defect down the scales.
Exactly. The familiar large to small scale direction of energy cascades in physics is not just some dynamical accident.
It's required.
It is the generic, required route by which closure defect is forcefully transferred into entropic dispersion. The cascade is just the universe dynamically redistributing the mismatch until it's gone.
But hold on. Let me stop you there.
Sure.
If the universe hates this geometric imbalance so much that it violently cascades it down into heat and entropy, how does anything stable ever form?
Right.
Like, why isn't the entire cosmos just an infinite chaotic soup of cascading defects?
Because the cascade doesn't always have to end in total thermal destruction.
It doesn't.
No. The universe does find permanent, stable states, but only when it hits stationary extrema.
Stationary extreme.
Right. When a constrained continuum is forced to resolve its closure, it violently eliminates all the unstable, non-admissible states, but it leaves behind a highly restricted family of persistent, permanent residues.
Okay. And what do physicists usually call those permanent residues?
We call that quantum mechanics.
Wow. And just like that, the entire paradigm shifts.
It really does.
We are stepping out of the realm of cascading turbulence and directly into the quantum world. The paper makes a staggering argument here.
It does.
It says that quantization, the famously weird fact that subatomic particles exist in discrete lock energy levels instead of a smooth spectrum that isn't some bizarre microscopic rule change.
No.
Quantization is just spectral closure.
It is the exact same mechanism we just saw in the fractal waves, but applied to a constrained continuum.
Right.
To really grasp this, we have to explore what the paper calls the closure-Rayleigh principle.
Okay, let's lay out the mechanics of this principle. What is the continuum and what is a constraint?
Imagine a purely continuous field, just a field of pure mathematical possibilities.
Okay.
If that continuum is unconstrained, any arbitrary wave or excitation can exist within it. It's an infinite canvas.
Anything goes.
Right. But the moment you apply a constraint, a physical boundary, a geometric limit, or a symmetry requirement, the continuum can no longer support just any random configuration.
Because the waves must now fit within the boundary.
Exactly.
Because if a wave doesn't fit, it destructively interferes with itself. It cancels itself out.
Precisely. Mathematically, the configurations that survive this brutal filtering process are the stationary extrema of a closure functional.
Which the paper denotes as script C of U.
Yes, they are the unique configurations that extremize the closure cost.
The closure cost. That phrasing is so critical, I feel like.
Oh, very much so.
Because it implies that it physically costs the universe effort to maintain an energy state.
It does. The eigenvalues, which in quantum mechanics we measure in a lab as the discrete separated energy levels of an atom, they are not just arbitrary numbers.
Right.
They are the literal closure cost of maintaining that specific stable excitation.
Wow.
Quantization is the spectral residue of constrained closure.
Okay, let's use an analogy here, because stationary extrema of a closure functional is definitely a mouthful.
It is, yeah.
It's like a cosmic game of musical chairs.
Okay, I can see that.
The unconstrained continuum is the phase when the music is playing, People are walking around the chair smoothly, continuous motion, anything goes.
Right.
But the music's stopping. That is the constraint, the boundary condition.
Yes.
When the music stops, you cannot stand halfway between two chairs. You cannot sit on a quarter of a chair. You have to snap instantly into a specific, discrete, predefined seat.
Right.
That violent snapping into a seat, it is quantization.
And that analogy maps perfectly to the paper's primary quantum example, the 1D infinite square well.
Ah, the classic particle in a box.
Exactly. It serves as the foundation of quantum physics. You have a particle, say an electron, confined to a strictly one-dimensional space between two absolutely impenetrable walls.
So the walls are the ultimate constraint. The music is stopped.
Exactly. Standard quantum mechanics tells us that the electron can only possess very specific energy levels, E1, E2, E3, and so on.
Right. It can never have an energy of E1.5.
Never. And if you ask a standard textbook why, it just says, because the wave function must be zero at the walls.
Which is mathematically true, but it doesn't feel like an explanation of the why.
Right. It lacks ontology. But the closure framework provides the deep ontological why.
So why?
Those discrete energy levels aren't arbitrary rules handed down from the quantum gods. The ground state, E1, is simply the most economical admissible closure configuration.
Economical.
Yes. It is the state that costs the universe the absolute least amount of energy to maintain while still perfectly satisfying the boundary constraints of the box.
It's the cheapest chair to sit in.
Exactly. And the excited states, E2, E3, they are progressively more costly closure states.
Because they have more waves.
Right. More peaks and valleys, meaning more kinetic energy, but they're still uniquely stable because they are strictly orthogonal to the lower ones. They are the next best economical options available once the easiest configuration is accounted for. The physical mode ladder of an atom is quite literally an ordered hierarchy of closure economy.
Okay, but I'm going to push back here.
Go ahead.
Because this sounds almost too neat.
Fair enough.
It's one thing to say a theoretical electron in a theoretical 1D box acts like musical chairs. I mean, a 1D box, it's just a line. It's easy math.
It is.
But we don't live in a 1D box. We live in a massive, sprawling, three-dimensional universe. How does this musical chair economy scale up to our actual reality? Like, does the 3D universe have a specific rule for how things are allowed to spin or vibrate?
It absolutely does. And the constraints of a 1D box translate directly into the constraints of rotational symmetry in our 3D world.
Right.
We just have to shift our thinking from linear boundaries to angular boundaries. And this introduces the concept of universal angular closure.
Universal angular closure, which tackles one of the biggest questions in all of science. Why is the universe 3D? Usually when you ask a physicist why there are three spatial dimensions, you get this anthropic answer, right?
Right, the anthropic principle.
Like, well, if it were 2D, complex biology couldn't exist, and if it were 4D, planetary orbits would be unstable, so we wouldn't be here to ask the question.
Which is true.
It is true, but it feels like a massive cop-out. It doesn't explain the structural reason.
Right, it's a philosophical observation, not a mechanical cause. This paper, however, provides a rigorous closure-theoretic derivation of 3 dimensions.
Wow.
Whenever you have a 3D system with rotational symmetry,
Like an atom holding electron orbitals.
or a spherical resonant cavity, or the massive harmonic structure of a pulsating star, the admissible angular modes cannot happen randomly. They must organize themselves into strict shells.
Shells. Anyone who took high school chemistry will recognize this, right?
Yes.
The SPDF electron orbitals.
Exactly. And the paper identifies the universal mathematical law governing these exact shells.
What is it?
It's the 2L plus 1 shell law.
2L plus 1.
Yes. For any given angular momentum level, which is denoted by L, the number of available linearly independent spatial modes is exactly 2L plus 1.
Okay, so if your angular momentum L is 0, the math says you have 2 times 0 plus 1, which equals 1 mode.
Right. That's the spherical s orbital. There's only one way to be a sphere.
Got it. And if L is 1, you have 2 times 1 plus 1, which equals 3 modes.
And that's the p orbital.
Shaped like dumbbells pointing along the x, y, and z axis.
Exactly. And this 2L plus 1 rule applies universally, scaling up infinitely.
But what makes this uniquely tied to 3D space? Like, couldn't this happen in other dimensions?
That is the key question. To understand why 3D is special, the paper analyzes the exact mathematical consequences of rotational closure in other dimensions,
Okay.
and it definitively identifies 3D space as the balanced regime of rotational closure,
Balance between what?
between being severely under-resolved and hopelessly overpopulated.
Okay, break that down. Under-resolved first.
If you attempt to build a universe in two-dimensional space, angular closure is under-resolved. There just isn't enough dimensional freedom, enough orthogonal directions to create a genuine hierarchical shell ladder. The symmetry is too tight, too restricted.
So a 2D flatland atom wouldn't have enough geometric room to build the complex chemistry needed for varied interactions.
Exactly. It's too simple.
Okay, so 2D is out. The musical spheres are too basic. What if we go bigger? What happens to the math in four-dimensional space?
In 4D and above, the geometric mechanisms drastically change. The angular sectors become immensely overpopulated.
Overpopulated.
Yes. The number of possible rotational modes proliferates superlinearly. You get a massive, uncontainable explosion of available states for the waves to occupy.
Because in 4D, you have entirely new planes of rotation that are independent of each other.
Yes.
The degrees of freedom explode geometrically, but the constraints only grow linearly.
Exactly. The system completely loses its minimal...
So it's spectral economy.
Yeah. Yes. It is no longer an efficient way to store energy. The Pauli exclusion principle, which keeps electrons from piling up on top of each other, would struggle to maintain rigid structure because the angular sectors are so incredibly vast.
I see. It's like having a concert hall with 1,000,000 chairs, but only 3 people.
That's a great way to picture it.
It's chaotic. There's no tight structure, no forced economy. The electrons wouldn't form the rigid, predictable chemistry we rely on. They'd be lost in a massive, overpopulated angular void.
Exactly. 3 dimensions is the unique Euclidean dimension, where the shell multiplicities are fully hierarchical, yet they only grow linearly.
Wow.
It is the perfect, absolute sweet spot of structural economy.
And this ties into a concept the paper calls the pi threshold principle, which absolutely melted my brain when I read it.
It is a profound geometric observation.
It really is.
The paper proposes that pi is not merely the ratio of a circle's circumference to its diameter.
Right.
Pi is the canonical theoretical measure of perfect rotational completion.
Perfect rotational completion.
Yes. If a mathematical system wants to optimize both rotational completion and minimal spectral economy simultaneously, the mathematical ideal benchmark is set by pi.
Roughly 3.14.
Exactly.
But the universe cannot physically build a space with 3.14 dimensions.
No.
Because we just established that non-integer dimensions are fractals. They are partial closure states. They are the 63% built bridges.
Right. They restrict movement.
The universe needs a solid integer dimension to fully close the manifold and allow free transport of energy.
And the number 3 is the absolute nearest integer realization of that 3.14 benchmark.
That is stunning.
3D space is the closest the physical universe can possibly get to perfect economical rotational closure without spilling over into the chaotic, overpopulated void of higher dimensions.
It's just so elegant, but wait.
Yes.
If 3D is the perfect balance, the optimal economical state for physical matter, why does the math even allow for 4D, 5D, or 8D?
This raises an important question.
Right. Are those higher dimensions just mathematical garbage?
Yeah.
Abstract fantasies on a chalkboard? Or do they hold something profound that the universe actually uses to build reality?
They are far from mathematical garbage. They are the hidden scaffolding of reality.
The scaffolding.
Yes. They represent the next rungs on an ontological ladder. And this takes us into the deepest, most theoretical part of the paper.
The 3-8-24 exceptional symmetry corridor.
Exactly.
Okay, we've established that 3 is the balanced rotational shell dimension. It's where physical space lives.
Right.
But the paper points out a specific geometric sequence that dictates the very structure of mathematics and high-energy physics.
The sequence is 3, 8, and 24.
It jumps drastic.
It does, because these numbers represent successive, distinct thresholds in the organization of admissible structure.
Okay.
We know 3 is the threshold of balanced shell emergence, but what happens at 8?
Right. What happens at 8?
8 dimensions mark the threshold of exceptional symmetry amplification.
Okay, we need to unpack the mechanics of 8D, because this is where standard intuition completely fails. What is happening in 8 dimensions that doesn't happen in 4 or 5?
In 8D, mathematical structures arise that are utterly unique across all possible dimensions.
Like what?
You have the octonions, which are the last of the norm division algebras.
Okay.
You have the Hopf fibration mapping a 7-dimensional sphere to a 4-dimensional sphere.
Sure.
But most crucially for physical reality, you have spin triality.
Spin triality. Okay, let's break this down. Triality means a 3-way symmetry, right? And the 3-way mirroring.
Exactly. In standard physics, we describe reality using very different mathematical objects.
Like vectors.
Right. You have vectors, which describe directions in space, like how fast a car is moving and in what direction.
Okay.
And then you have spinors, which are deeply weird quantum objects that describe the internal angular momentum or spin of particles like electrons.
And normally a vector and spinor are completely different mathematical animals.
Completely different. They live in different spaces, they have different dimensions, they transform differently.
They are an apple and an orange. You cannot rotate an apple into an orange.
Precisely. But in exactly 8 dimensions, something miraculous happens.
What?
The mathematical space of vectors, the space of left-handed spinors, and the space of right-handed spinors all converge.
We converge.
They all have exactly the same dimension, 8. And because of this perfectly aligned convergence, there emerges a unique, exceptional symmetry triality that can rotate these 3 completely different mathematical objects into one another as if they were the exact same thing.
That is wild. It's like finding a magical room where an apple, an orange, and a banana can all perfectly swap identities.
Yes.
But that room only exists on the 8th floor of the building.
That's a brilliant way to put it, and that's why 8 is an amplification threshold.
Right.
The symmetry becomes exceptionally rich, allowing forces and matter fields to mathematically unify.
Okay. And then the sequence takes a massive leap to 24.
Right, and the text calls 24 the exceptional completion regime.
Exceptional completion. So what's happening at 24?
To understand 24, we have to look at how geometry packs together.
Packing. Like stacking spheres.
Yes. In 3-dimensional space, we have the platonic solids, the cube, the tetrahedron, etc.
Right.
In 4-dimensional space, there are regular convex polytopes. One of them is called the 24 cell.
A 24 cell.
It has 24 vertices, and its boundary is made of 24 octahedral cells. It is a completely unique geometric object. It has no analog in any other dimension.
None at all.
None. And when you jump to 24 dimensions,
Yeah, what happens there?
in 24 dimensions, you find the Leech lattice.
Ah, the Leech lattice.
This is an incredibly famous mathematical structure. It's the phenomenally dense, exceptionally symmetric way to pack 24-dimensional spheres together so they lock perfectly into place.
Like the ultimate puzzle.
Yes, it's the absolute ultimate peak of modular closure and exceptional packing efficiency.
But again, I have to play the skeptic here.
Please do.
Is this just numerology? Like, oh, cool, these numbers 3, 8, and 24 pop up a lot in high-level string theory and abstract math.
It's a common criticism.
Right. Why should I care about an 8-dimensional spinning apple or a 24-dimensional sphere packing puzzle if I am sitting in a 3D chair drinking a 3D cup of coffee?
Because this sequence, 3, 8, 24, is an ontological threshold sequence.
Ontological, meaning
Yeah.
about the nature of being.
Exactly. These aren't just bigger numbers in a math textbook. They represent entirely new modes of structural being.
Wow.
They are the formal skeleton of what is structurally possible in the universe. Harmonic geometry, these highly symmetric mathematical structures in 8 and 24 dimensions, defines the absolute limits of symmetry.
But they don't stay in the abstract realm.
Exactly. The universe doesn't leave them hovering in some abstract mathematical ether.
Right.
These higher dimensional symmetries actually transmit downward.
They transmit downward.
Yes, they project their complex rules into lower ontological layers. They filter down into our 3D world to create the actual physical stuff of our universe.
So the math becomes matter.
Yes. The threshold at 8 transmits exceptional symmetry downward. The threshold at 24 transmits global completion downward. They are the mathematical enabling conditions for physical structure.
So the universe starts with these abstract, perfect mathematical possibilities in 8 and 24 dimensions, and then it forces them to descend, filtering them down into the tight constraints of our 3D reality.
Perfectly stated.
Which brings us perfectly to the mechanism of that descent, the gauge versus matter bifurcation.
This is where it all comes together.
We're finally at the point where purely abstract mathematical symmetry becomes a physical, tangible particle. How does a piece of math become a thing?
It happens through what the paper describes as the parent ontology.
The parent ontology.
Yes. Once an internal symmetry channel, one of these mathematical possibilities transmitted from the higher dimensions, becomes closure stable under the relational constraints of our 3D universe, it faces a fundamental, unavoidable choice.
It has to pick a path.
It has to stabilize physically, and it has 2 and only 2 persistence modes available to it.
It bifurcates. It splits down 2 distinct paths.
Yes. The first path is the gauge branch.
The gauge branch.
If a symmetry takes this path, it chooses to remain extended and relational.
Extended.
It distributes itself across space. It becomes the medium of interaction, dictating how other things communicate.
Ah, These become the physical forces of nature. The
Exactly.
gauge fields,
Yeah.
electromagnetism, the strong force, the weak force.
Exactly. And the paper explicitly maps these forces to what it calls the unitary ladder of closure economy.
Okay.
It's a hierarchy of how a symmetry can act relationally. The simplest, most economical internal symmetry is phase preservation.
Phase preservation.
Mathematically, this is the U1 symmetry group.
And what does U1 actually do physically?
It dictates that the underlying quantum phase of a particle can shift globally without changing the physical laws.
Okay, and what is the physical manifestation of that?
The extended relational rule of that U1 symmetry is the electromagnetic force.
Light itself.
Yes.
Okay, so that's the simplest rule. What's the next step up the ladder?
The next most economical closure is doublet preservation, governed by the SU2 symmetry group.
Doublet, like pairs.
Right. This involves symmetries that can rotate a pair or the doublet of particle states into each other.
And what does that become?
The physical manifestation of this extended rule is the weak nuclear force.
Which governs radioactive decay.
Exactly. And finally, you reach triplet closure, the SU3 group, which rotates 3 distinct color charges.
The strong force.
Yes. This manifests as the strong nuclear force, the unimaginably powerful glue that holds the quarks inside protons and neutrons together.
So the fundamental forces of nature are literally just different mathematical symmetries, choosing to remain extended and distributed across space as rules of interaction.
That's exactly what they are.
That's amazing. Okay, so what's the second path?
The second path is the matter branch.
A matter branch.
Instead of remaining extended and relational, the mathematical symmetry condenses.
It condenses.
It forcefully embodies itself locally into a tightly bounded, stable excitation.
These become the physical particles.
Yes.
The fermions. The electrons, the quarks, the physical stuff that builds atoms.
Yes. Gauge persistence is distributed symmetry continuation. Matter persistence is localized symmetry embodiment.
Wow.
They are 2 manifestations of the exact same underlying parent ontology.
I have an analogy for this bifurcation that I think perfectly grounds it.
I'd love to hear it.
Let's think about the game of chess.
Okay, chess.
Both branches of this physical reality come from the exact same underlying logic of the game. The grid, the geometry, the potential.
Right.
The gauge branch is the rules of how the pieces are allowed to move. The rule that a bishop must move diagonally across the board.
I see.
That rule is extended. It applies everywhere on the board simultaneously. It's relational. It dictates the interactions of the game. It is invisible, but it governs everything.
A perfectly distributed relational structure.
Right. And the matter branch is the physical carved wooden pieces themselves.
Yeah.
The solid wooden knight sitting on square G1. It is the strictly localized, bounded embodiment of the game's logic. The force is the invisible rule, the matter is the physical piece.
Right.
But they both emerge from the exact same underlying parent logic of the game, just expressing their existence in 2 different ways.
I love that analogy because it perfectly captures the elegance of the parent ontology.
It really makes it click.
It does. The standard model of particle physics, with its specific gauge bosons carrying the forces and its specific fermions making up the matter, it isn't just a random assortment of fields we happen to have discovered by smashing things together in particle colliders.
Right. It's not arbitrary.
The paper argues that the standard model is the necessary structural residue of closure selection dynamics.
And the necessary residue.
The universe takes harmonic admissibility from higher dimensions, subjects it to the constraints of our 3D space, and the stable remnants bifurcate into the rules of the board and the physical pieces on the board.
That is beautiful. It makes the universe feel so deeply logical, so much less arbitrary.
It really does.
But wait.
Yeah.
If the physical wooden chess piece is just a localized, condensed piece of mathematical symmetry.
Right.
If it's just a rule that decided to fold itself up into a little bounded point, why does it have weight?
Mm-hmm.
Why does a bowling ball feel so heavy? Why do things have mass at all?
And that profound question takes us to the final revelation of the paper, the weight of existence, the mechanics of mass, generations, and decay.
Because in standard physics, mass is just a parameter, right?
Right. It's a property we just plug into an equation.
We say the Higgs field gives particles mass, but the specific values of those masses, like why an electron is so incredibly light or why a top quark is massively heavy,
Right.
They're just empirical numbers we measure.
Exactly. We have no underlying theory for why they weigh what they do.
None.
But the closure framework offers a complete structural redefinition of mass.
What is it?
Mass is not an arbitrary property attached to a field. Mass is the persistence cost of localized closure.
The persistence. Okay, let's dig into that mechanism. What is it costing?
Remember, the natural, most economical state of a symmetry is the gauge branch.
To be extended.
Right, to be distributed and relational like a force field. To force that symmetry to condense, to localize it tightly into a bounded entity, a matter particle, takes an immense amount of work. It actively resists this condensation. It naturally wants to disperse and unknot itself.
Because the universe has an entropic gradient, it wants things spread out.
Exactly. The deeper you localize the symmetry, the more tightly you knot that geometry into a concentrated point of closure.
The higher the cost.
The exponentially higher the energetic cost to maintain that state against the universe's natural gradient.
So the physical mass of a particle is literally just the universe's ongoing energy bill for keeping that specific symmetry knotted up in that specific location.
Precisely.
Wow. So a bowling ball is heavy because it is made of trillions of tiny, incredibly tight geometric knots, and the universe is constantly expending energy just to prevent those knots from springing open and dissolving into pure distributed force fields.
Yes, that is exactly what mass is.
That is mind-blowing.
And this localized knotting naturally creates what the paper terms generational strata.
Generational strata.
In the standard model, physicists have long been baffled by the fact that there are 3 distinct generations of matter.
Right. You have the first generation.
The up and down quarks that make protons, and the electron. They are very light and completely stable.
That's the stuff that makes up everything we interact with.
Right. But then you have a second generation.
The charm and strange quarks and the muon.
Yes. They act exactly like the first generation, but they are much heavier and highly unstable.
And then a third generation.
Top and bottom quarks and the tau particle. They are unimaginably heavy and violently unstable, decaying in fractions of a second.
And standard physics has never explained why there are 3 identical copies of the matter particles, just getting exponentially heavier each time.
Never. But the closure framework does.
How?
It explains this through closure depth stratification.
Stratification.
Localized closure isn't a smooth, continuous sliding scale, just like the quantum energy levels in the box we talked about earlier.
The musical chairs.
Exactly. Localization organizes into stable bands or strata of varying depth.
Heck.
The first generation of matter represents a shallow closure state. It requires a relatively low persistence cost, so it has low mass.
And because it is minimally localized, it remains very close to the coherent harmonic regime.
Exactly. It is inherently stable.
And the second and third generations are the deeper knots.
They are far deeper closure states. They are forced into much tighter, more restrictive localizations, which requires a massive persistence cost, hence their enormous mass.
Right.
But because they are forced into such incredibly deep, condensed states, they are pulled far away from the stable, coherent, harmonic regime. They are structurally precarious.
Which brings us to the mechanism of particle decay, driven by what the text calls the closure gradient.
Yes, the closure gradient.
Okay, walk me through this.
The universe possesses a fundamental structural direction. Heavier, deeper strata are less coherent. They cost too much.
The energy bill is too high.
Right. If there is a transition channel mathematically available, a pathway allowing a tightly knotted configuration to step down into a shallower, cheaper stratum, the system will inevitably take it.
It will just drop down.
Yes, this is the underlying structural reason behind particle decay and particle mixing.
So a heavy tau particle, which for you listening is essentially just a supermassive electron from the third generation, is a deeply, deeply knotted up piece of mathematical space.
Yes.
It costs a massive amount of energy to keep it tied that tight. Because it's so tight, it's under immense structural tension.
Exactly.
It's inherently unstable. It desperately wants to unknot itself. So it decays.
It relaxes.
It relaxes along the closure gradient, emitting bursts of energy, transitioning down through available quantum channels until it relaxes all the way down into the lowest possible state.
A stable first-generation electron.
Exactly.
In this view, particle decay is not just some random probabilistic event dictated by a quantum roll of the dice.
It's a deterministic process of closure relaxation.
Yes. It is the matter branch dynamically evolving toward shallower, more coherent, cheaper energetic regimes.
And what happens when the knot unwinds as far as it can go? When it hits the bottom of the gradient?
It reaches the state of stable matter.
Stable matter.
The paper defines stable matter, like the electron or the up quark, not just the stuff that happens to have a long half-life.
But as the absolute rock-bottom ground state of the closure gradient.
Yes, it is the geometric configuration where no downward transition channels are mathematically left. It is the absolute minimal localized embodiment of closure-stable symmetry.
Once it reaches that state, it can unknot no further.
Exactly. It persists permanently as the terminal residue of the universe's attempt to find structural balance.
Wow. Let's take a breath and look back this massive journey we just took.
We covered a lot of ground.
We started with fractal shapes that we previously thought were just infinite jagged lines on a computer screen.
Right.
But we realized they are actual physical systems, desperately trying to find geometric closure, stabilizing as fractional realities.
Then we saw how wave energy, trying to navigate those incomplete spaces, is forced to find spectral closure.
Right. This negotiation between space and energy leads directly to the quantization of states.
The universe playing musical chairs to find the most economical, stable modes of existence.
From there, we scaled up the dimensions. We saw structurally why 3D is a perfectly balanced home for rotational geometry.
Avoiding the severe under-resolution of 2D and the chaotic overpopulation of 4D?
Yes, and we saw how the exceptional mathematical symmetries operating in 8 and 24 dimensions act as a formal skeleton.
An ontological ladder.
An ontological ladder that transmits abstract structural possibilities downward into our reality.
Possibilities which, once forced to physically stabilize in our highly constrained relational universe, bifurcate.
They split into two paths.
The distributed extended rules of the gauge forces.
In the localized, heavily condensed pieces on the board, physical matter.
And finally, we saw that the physical mass of those pieces is nothing more than the energetic cost of existing.
The literal cost of remaining localized against the universe's natural gradient of dispersal.
With particle decay simply being the natural relaxation of deeply knotted space into the stable, minimal matter that makes up you, me, the Earth, and the stars.
Wow. If you are holding a coffee cup right now, or resting your hand on a desk, or just feeling the physical weight of your own body, don't just think of it as a solid chunk of stuff.
It's so much more than that.
Think of it as a localized embodiment of closure-stable symmetry. You're made of condensed pieces of math,
Deeply knotted symmetries.
maintaining their physical existence against the universe's gradient of dispersal. You and everything around you are the stable residue of a cosmic balancing act.
We've seen how the deep geometric rules of 3, 8, and 24 dictate the exact architecture of closure and literally birth the physical reality we experience every day.
We have.
But understanding this framework leaves us with a rather haunting thought to explore on your own.
Oh, what's that?
Well, if our entire physical reality, the standard model, the forces, the dimensions, is just the stable residue of these higher mathematical symmetries trying to close themselves,
Right.
what incomplete partial closure structures are forming right now at scales we can't yet see, waiting for their own threshold of completion to birth entirely new physical laws?
Wow. What a profound thought to end on. A universe still mathematically negotiating its own existence. Thank you so much for joining us on this massive deep dive into the source material. Remember to question the categories, look past the visible layers of reality, and as always, stay curious.